Hello friends, welcome to Knowledge Galaxy to rediscover the basics with Mayank Tiwari, a premier coaching and training channel dedicated to metallurgy studies and consultancy. Established to cater the needs of students, degree, diploma and AM/IIM metallurgy, competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries, working and aspiring professionals and whosoever seeking knowledge and information about various subjects and topics of metallurgy, ferroalloys, operational process optimization, productivity improvement analysis, etc. To impart practical industrial knowledge as per your specific requirements via tailor-made training sessions for your colleagues, employees and students, please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +919907144101 for scheduling and organizing the sessions at your place or via video conferencing. My dear friends, nowadays technology has improved so much that actual physical distance doesn't matter anymore. You can get all your doubts cleared by sitting at your home, at your comfort zone, just by contacting me over WhatsApp or phone, so that for your benefit, please do contact me for any of your doubts. My dear friends, I have made so many videos which are available on my YouTube channel. So I request you to visit my channel regularly and repeatedly and watch all the videos available there, so that you can gain maximum knowledge about the subject and topics, and also request you to watch all my videos from start to finish, so that you can gain the maximum and complete knowledge about the topic. My dear friends, as you know that training is costly, but not to train is still costlier. And when you are not having complete knowledge or don't get any information about the topic which you need to know, so you can contact me. If you don't find anyone who can help you to clear your doubts, you do contact me as soon as possible. And so right now in this video I am discussing about In this video, I am going to describe about yet another very important aspect of high carbon ferrochrome production in submerged arc furnaces. My dear friends, as you know that ferroalloys production process via submerged electric arc furnace route is a very high energy intensive industry, and process operation consumes too much of energy in the form of electrical energy, and to save the energy we must incorporate new things and operational procedures, so that the energy consumption in the ferroalloy production can be brought down. So the topic of current presentation is optimization of specific power in high carbon ferrochrome production. So I hope this topic will definitely elaborate all the details and procedures how to reduce the specific power consumption in high carbon ferrochrome production. And I hope that this presentation you will definitely like it, and also will try to incorporate in your plant operation. So before I proceed in this presentation, I would like all of you to watch and observe the message given in the next slide.
have seen and observed in the video that no water can be filled in the pot if the pot is not aseptic, and also if the pot is already filled. The water can only be filled when there is some space in the pot. So my dear friends, I request you to keep your minds open for receiving the information so that you can receive the information correctly and gain the knowledge. But if you feel that you are already having much knowledge or more knowledge, or if you are not receptive towards receiving the new knowledge or information, you cannot gain anything. So for gaining new knowledge and information, please keep your mind open and be receptive for the new knowledges always. My dear friend, I am having one of very important announcement for you all. The information which I want to share is that if you want to advertise your products, services, company or anything else on my channel, then please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 44101 for putting your advertisements in my forthcoming videos. My dear friends, as you all are aware that advertising in the YouTube channels is very common and very fruitful method of approaching to the mass volume of viewers. So you can contact me for putting your advertisements in my forthcoming videos. I hope the messages which I have conveyed in the previous slides is very much clear to you all. So now let's start the present presentation. Production of ferrochromium in the submerged arc furnace is highly energy intensive. As I have mentioned it many times that the energy consumption in production of ferroalloys via submerged arc furnace route is very high, and it is the major cost portion of the total production cost, and it consists of approximately 40 to 45% of the total production cost of any ferroalloy produced via submerged arc furnace. So we all operational personnel must always try to bring down the specific power consumption in the production of all ferroalloys produced, and this substantially gives savings for the company. So we all must try to optimize our processes, and different technologies, different processors and different operational procedures have been implemented worldwide to bring down the specific power consumption of the alloy produced. So here I am also going to describe few more operational procedures which can be implemented to bring down the specific power consumption in high carbon ferrochrome production. Several process ways have been attempted to reduce the specific energy consumption in the production of this alloy. An exhaustive understanding of the thermochemical features of the production process can be used to reduce the specific power consumption significantly. The knowledge can be used to reduce the energy drain through undesired reactions in the process can be minimized. Plant trials have shown that specific energy consumption up to 100 kWh per ton of hot metal can be obtained by adopting this strategy. As I have mentioned earlier that specific power consumption and electricity cost consists of approximately 40 to 45% of the total production cost of the alloy. So this much saving of energy per ton can give a substantial amount of saving in the form of money for the company. The process requires modification in operation practice and does not require any capital investment, unlike other processes adopted for reducing specific power consumption. The principle of thermochemistry involved in this process development and results of plant trials are discussed in detail. The specific power consumption in the production of ferrochromium can be as high as 3.8 megawatt hour per ton of hot metal and sometimes exceeds 4 megawatt hour per ton. Considerable efforts are made in industries to reduce the specific power consumption by adopting novel processes and practices. A thorough analysis of the thermochemistry of the process shows that there is considerable scope to exploit the energy distribution and optimize the specific power consumption. The hot metal produced in the process contains chromium and iron as the major constituents. Apart from these, it contains significant levels of silicon. Though silicon is desirable in the hot metal at certain levels to improve its purity, at higher levels it is not only undesirable, being a major impurity, it also leads to considerable drain of energy. If the silicon level in the hot metal can be brought down by 1 percentage point, say from 3.5% to 2.5%, this can result in a saving of 3,750 megawatt hour of energy per annum for a plant producing 50,000 tons of ferrochromium every year. The thermochemical nature of the process and the thermal profile prevailing in the furnace can easily facilitate a reduction in the specific energy consumption through minor modifications in the operational procedures. Reduction reaction. Let us consider the different reduction reactions happening in the production of high carbon ferrochrome. Table 1, which is depicted in the next slide, gives a typical analysis of the charged material used in the production of ferrochromium. The charge consists of a mixture of chromate ore, coke and quartz as a flux. A typical temperature profile in the submerged arc furnace, that is HC, has been derived through mathematical modeling. The temperature varies from about 2000 degrees Celsius at the tip of the electrode to about 250 degrees Celsius at the top of the charge bed. Investigations on the reducibility of the chromate ore shows that iron starts getting reduced at 900 degrees Celsius. The reaction is usually complete at 1000 degrees Celsius. The reduction of chromium commences at 1200 degrees Celsius and is completed by the time the charge reaches 1400 degrees Celsius. The rate of reduction of chromium is enhanced by the reduction of iron due to the formation of alloy of iron and chromium. Therefore, as the charge descends through the various temperature zones of the SAF, its composition changes due to various reduction reactions occurring to various extents in the different zones. It is observed in laboratory experiments that reduction of silicon that is present in the ore in quartzite and in the ash of coke can get reduced at temperatures as low as 1400 degrees Celsius supplied by the formation of the ferrochrome silicon alloy. So this is the table 1 which depicts the charge used in the production of ferrochromium tons per day. This is a typical consumption, may vary from plant to plant and capacity wise. So all these nomenclatures are mentioned here. You can pause the video and observe the table contents. Okay, now let's move on. Slag metal equilibrium. This is very important from the operational control aspect. As the charge descends through higher temperature zones above 1600 degrees Celsius, liquid slag is formed. The interaction between the slag and metals is rapid and equilibrium is reached. Therefore, the composition of the metal is determined by the equilibrium between the two phases above this temperature. The composition of the metal in equilibrium with the slag at different temperatures is given in table 2 in the coming slide. A striking feature of the equilibrium compositions of the metal is that silicon is not present in the hot metal at temperatures less than 2000 degrees Celsius. The zone where temperature is equal to or above 2000 degrees Celsius is close to the electrode tip. So this is the table 2, which gives chemistry of metal in equilibrium with slag, and it is in mass percentage. You can pause the video and observe the different contents of the table.
My dear friends, just to interrupt you all, here I would like to emphasize on some special important aspect of Knowledge Galaxy. Here, specialized subject-wise coaching classes and topic-wise doubts clearing are available. I am available for all of you to clear all your doubts, and especially for Diploma Engineering, Metallurgy and Mechanical students, Indian Institute of Metals, that is IIM, Part 1 and Part 2, and competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries, working and aspiring professionals. Here I would like to emphasize that whatever queries and doubts you are having in your mind regarding any subject or topic of metallurgy or any other ferroalloys production, operation, maintenance, so you can contact me for getting your doubts cleared. I will try to provide you accurate knowledge and to the best possible extent at the very shortest period of time, so that you can gain your knowledge, clear all your doubts, so that you can grow in your career, whether it is academic career, whether it is professional career, and so that you can develop and grow. So to continue with, here complete syllabus coverage for the students aspiring to appear in the forthcoming semester exams, that is December or June, I will be providing you all. So please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 44 101 for scheduling and organizing the classes or getting informations to clear your doubts via video conferencing, call or WhatsApp. My dear friends, you might have encountered that you might have been having many of the doubts regarding process, technology, why they are doing, why it is done, how it is done. So, and if you don't find any answer to them and nobody is there to guide you properly, so my dear friends, I am here available to guide you all, to make you know and grow, and so that you don't have any doubts related to your process, products, technology, syllabus, and I will make sure that all of your doubts get clarified and you know the topic and subject very well and completely. So again, let's move on.
Okay, now coming back. The charge can be assumed to move uniformly through the cross section of the SAF. Since Silicon is produced excessively in the high temperature zone where the temperature is 2000 degrees Celsius or above. It is possible to predict the size of the zone from mass balance for silicon between the charge and the metal and slate produced. The level of silicon in the hot metal produced can be shown to be a linear function of the high temperature zone of the form percentage silicon hot metal is equal to X into silicon B. This is the equation number 1, where percentage silicon HN is the percentage of silicon in the hot metal. Percentage silicon B is the equilibrium level of silicon in the hot metal in the high temperature zone expressed as a mass percentage. X is the relative size of the high temperature zone. As indicated above, the size of the high temperature zone can be predicted from a mass balance for silicon. The size of this zone predicted through this model was in good agreement with that predicted based on the model of thermal profile in the SAF. Good agreement between results obtained using the two different models enhances the applicability of the model. Data were collected from different industrial plants producing ferrochromium. The size of the high temperature zone was correlated with the level of silicon in the hot metal in each case. The following expressions were obtained in the 4 cases studied. First one is percentage silicon hot metal is equal to minus 0.04 plus 14x. Next is percentage silicon hot metal is equal to 0.24 plus 12x. Next is percentage silicon hot metal is equal to minus 0.43 plus 14x. And percentage silicon hot metal is equal to minus 0.32 plus 15x. Two of the cases above are illustrated in figure 1 and 2, which are coming in the next slide. It is obvious that there is a linear relation between the size of the high temperature zone and the level of silicon in the hot metal. The intercepts in the expressions are negligible and close to 0. Hence, the expressions are consistent with that derived theoretically in expression 2. Such an excellent agreement between the model and plant observations enhances the utility of the thermochemical model and its role in devising appropriate operational practice to maximize the process efficiency. So this is the figure 1, which shows the silicon level in hot metal as a function of the size of the high temperature zone in case 1. So you can observe that this is a linear relation which I have just explained. And this is the figure 2 for the case 2. Same linear relation is observed. So now let us discuss about control of energy consumption. If the extent of reduction of silicon in the charge can be decreased by utilizing the energy and coke available for the reduction in the charge, the specific energy consumption can be decreased. This is very important, so I am just repeating it once again. If the extent of reduction of silicon in the charge can be decreased by utilizing the energy and coke available for the reduction in the charge, the specific energy consumption can be decreased. From expressions 2 to 6 above, it can be seen that this objective can be achieved if the amount of silica passing through the high temperature zone can be reduced. The thermochemical model and the mathematical expressions derived above retaining the spatial dimensions of the furnace to the extent of silicon recovery provide an excellent tool to achieve this. Silica in the chart comes from quartzite, ore and coke. About 50% of the silica charge is in the form of quartzite. The conventional procedure of ferrochrome production is mixes all the charged materials and charges them uniformly across the cross section of the furnace. If the quartzite present in the burden is segregated and distributed selectively, it can be ensured that the energy and coke would automatically be utilized in greater recovery of chromium, resulting in a reduction in specific power consumption. So now let us discuss about the plant trials done. Plant trials were conducted at an industrial furnace to validate the model. This furnace had 6 tubes feeding the raw materials. 3 of the tubes were located such that each pair of electrodes had a tube in between them. The other tubes were on an outer circle such that the center of the tube, that of one of the electrodes, and the center of the furnace were collinear. From the geometry and dimensions of the furnace and tubes, it was estimated that about 61% of the material charged through the inner tubes passed through the high temperature zone and 29% of the material charged through the outer tubes passed through the high temperature zone where the temperature was 2000 degrees Celsius or above. A typical charge contained about 72 to 78% chromate ore, 15 to 22 weight% coke, and 4 to 7 weight% quartzite. The charge was divided into 2 portions. The first portion had the same proportion of ore and coke as above, but the proportion of quartzite was reduced. This was balanced by adding the same quantity of quartzite to the second portion of the charge. Thus, the second portion had the same proportion of ore and coke as the first portion, but had a higher level of quartzite. The first portion of the burden was charged through the inner tubes and the second portion through the outer tubes during the production operation. Data were collected on the chemistry of the raw materials, that of hot metal and slag, and on power consumption during the trials.
Before proceeding, if you like my content and have not subscribed to my channel till now, then please subscribe to my channel so that you can watch all the videos available in my channel list, and also press this bell icon so that you can get the notification of new videos promptly and don't miss anything. In case you want to thank me and support me so that I can get further motivation to do better in future, you can just simply send me this special thanks, super thanks, by selecting any of this amount of your choice, whatever you feel like suitable to you. You can just buy this and send to me. This will help me to do further better. You can select any of the payment methods of your choice and then send me. This will motivate me to do further better in future. Thank you.
So now let us discuss about the results and discussions. To evaluate the performance of the process during the trial period, the average power consumption for a period of 1 week preceding the trial period was taken as a reference. The other operation parameters of the process, such as the nature and quantities of raw materials charged, the power supply characteristics, etc., were maintained constant during the trial and reference periods. The average specific energy consumption during the trial period was compared with the average for preceding week. During trial 1, the average energy consumption was 3.317 megawatt hour per ton hot metal. The average for the preceding week was 3.439 megawatt hour per ton hot metal. During the second and third phase of the trials, the average specific energy consumption was 3.362 megawatt hour per ton hot metal. The average specific energy consumption for the preceding week was 3.466 megawatt hour per ton hot metal. Table 3 shows the level of silicon in the hot metal during the trial period compared with that obtained during the reference period. The table is shown in the next slide. It is obvious that the modified operation practice decreased the level of silicon considerably. And table 4 gives the fraction of the total carbon charge that was used in the reduction of SiO2 to Si. So this is the table 3 which shows the silicon level in hot metal during the trial period. So you can pause the video and observe the contents of the table. And this is the table 4 which shows the fraction of carbon consumed in recovery of silicon. As usual, you can pause the video and observe the contents. The same principle can be applied for the optimization of specific power consumption in the production of other ferroalloys. A case which is very similar to the above is the control of the reduction of A2O3, that is alumina, in the production of ferrosilicon. Adopting the process illustrated above, the specific power consumption can be lowered here also. Other similar cases in the production of ferroalloys can be explored. So this table also gives the fraction of silicon recovered out of the total charge, the above table mentioned. It is demonstrated that the recovery of silicon decreased considerably during the trial period. This also released significant amounts of carbon for other reduction reactions. Hence, the specific power consumption decreased during the trial period. Now, let's have the conclusions of all these discussions. Modeling of the thermochemistry of the production of ferrochromium in the Sambar dark furnace showed that it would be possible to reduce the specific energy consumption in the production of the alloy by rationalizing the distribution of the charge. Plant trials were carried out to validate the model. The trials showed that it was possible to reduce the specific energy consumption by about 100 kWh per ton of hot metal produced by adopting this strategy. A similar process can be adopted to optimize the specific power consumption in the production of other ferroalloys also.
Dear friends, I am providing you all the informations free of cost which are available in my YouTube channel. So do help me by watching all my videos. Do subscribe my channel. Regularly visit and repeatedly visit my channel. Do watch all my videos, contents, like the content, share with your friends, and so that I also get motivated from each one of you as you subscribe to my channel. I am very much thankful to all my subscribers who believe in me, have subscribed my channel and like my content. So to motivate me further, please do subscribe my channel, increase the subscriber count, share with your friends so that others can also gain the knowledge. And my dear friends, all if you subscribe my channel, this will motivate me to do further better. So I hope you like the content and found the video worth. So again request you to please don't forget to like, share and subscribe the channel. Also remember to press the bell icon so that you can get the notification of the new videos promptly. My dear friends, here if you want to advertise about your product, services or company or anything else for gaining popularity in my channel, so you can contact me so that I can put your content for advertisement in my videos, forthcoming videos. So it will be a good platform to advertise. So do contact me as soon as possible. Thank you very much for watching this video till the end, and I am very much again thankful to all of you who helped me, who believe in me, and please do visit my channel regularly and repeatedly. Thank you very much again. See you in the next video. Thank you.